So our second calculus unit is on applications of derivatives, and the first thing that we look at is becoming better graphers. Yeah, I know everybody loves graphing, so we get to graph more. Because it was like only, what was it, only 60% of your units in grade 12 involved graphing. So you're probably going through a little bit of withdrawal. And so it is important after doing stats and probability and derivatives that we get back to graphing. So if you had 3x squared plus 12x minus 1, first of all, what is that? What shape? It's a parabola. How would you have graphed that in the past? Don't say with my graphing calculator. Do you remember what we did for graphing? That's grade 11 stuff, right? That's a while back. Do you remember like completing the square to find the vertex? So that's where you factor out the 3, which would leave you with the x squared plus 4x. And then in green there would be a space. And in that space, you'd have to say, well, how do I get that x squared plus 4x to be a perfect square, x plus 2 squared? And you might have remembered oh, my pens aren't working. We're going to have to go purple. Here we go. Divide by 2, and then square to get that number. Does that ring a bell? And then, why is it minus 12 for the other green number? If I added 4, why don't I subtract 4? Because I factored out that 3. That 3 multiplies to give you that 4. And so you've actually added 12, so we need to subtract 12. And then once we complete the square, you would know that the vertex is at minus 2, minus 13. Now, for our calculus method, what do we know about a vertex? Is that our vertex happens at a maximum or a minimum. And so our vertex will always happen, wow. Our vertex will always happen when the slope is equal to 0. So if we find our derivative, because our derivative gives us all of our slopes of any tangent at any value of x. And if we set our derivative equal to 0, look how fast we can get x equals negative 2. And once you've got negative 2, you can plug that value back into your original equation and get negative 2, negative 13. And you could find your vertex that way as well. Now, the nice thing about the calculus method is we don't have a completing the square method for x cubed graphs that could have one maximum and one minimum. But calculus can get both of those for us. Or if we had an x to the 4 graph, remember some x to the 4 graphs look like w's in the end? You would have 2 minimums and 1 maximum. And calculus can find those. So what we find in the past is all the way through, you start learning graphing, and now when you get to calculus, we learn an overarching technique that works for any graph. Instead of having, oh, y equals mx plus b is special for lines, and completing the square is special for parabolas, and this is what I do special for rational functions, and this is what I do special for this one. We can use all of those, combine them all into just one technique, which is nice. So some stuff about calculus. Calculus is about tangents and slopes of tangents. So what happens when we have the slope equal to 0? That means that we have a horizontal line. If the slope of the tangent line is 0, we would have a horizontal line. Now, if your derivative is bigger than 0, what does that mean? Well, that means that our slope is positive. And we're going to find out that whenever our slope is positive, that our functions are going to be increasing from left to right. So we know the direction that our graph is going. And of course, if the derivative was less than 0, then our tangent lines would be negative. The slope of our tangent lines would be negative. So, positive and negative slopes tell us where our functions are either increasing or decreasing. We say that a function is increasing if it goes up from left to right, or it rises from left to right. In other words, the y value increases as the x value increases. And we say that a function is decreasing if it goes down or falls from left to right. So you have the following graph. What we're going to do is we're going to draw on the graph. I'm going to use a blue pen to represent where it's increasing, a red pen to represent where it's decreasing. And we can see until we get to our local maximum, it's increasing. Then between that local max and the local min, it's decreasing. And then it's increasing after that. And one thing you can notice is if you pick any point on the blue section, so if I pick this point right here on the blue section, and I drew a tangent, can you see that the slope of that tangent line is positive? If I drew another point on another part of the blue line, and I drew a tangent, the slope of that tangent is positive. But any time I draw a point on the red part where the function is decreasing, I get a negative slope. So what this is going to help tell us is that if we can find our derivative, and we can find out where our derivative is positive and where our derivative is negative, we're going to know the direction that our graph is going. There we go. Just slide those away. So any line where it's increasing is going to have a positive slope, and anywhere where the graph is decreasing is going to have a negative slope. So we saw in the example that we started with that we could use calculus to find our maximum or minimum by getting the derivative and setting it equal to 0. Now we're going to be able to use calculus to tell us, well, what's happening on either side of that maximum or minimum? Where is it increasing? Where is it decreasing? So here's our first example. It's another parabola. You already know what this parabola looks like because you are parabola experts, right? Parabola experts go, oh, it's 2x squared, it's positive. Does it open up or open down? Opens up because it's positive, right? Finding the vertex, yes, you'd have to complete the square, but at least you know which way it's opening. Now, if we use our calculus, we can find our derivative really easy on parabolas. It's just going to be 4x plus 1. If we set our derivative equal to 0, we're going to find that that happens at -1/4. Now, in calculus, before we know what it is exactly, we call that a critical value because it's either going to be a maximum or a minimum. In this case, since you already know your parabola opens up, you know that it's going to be a minimum. But if we look at that point, we could draw a sign diagram. Now, you did these sign diagrams a little bit when you looked at inequalities. It's sort of that same idea. We put our critical value on a number line. Here we've got -1/4. And then you can plug in test values above -1/4 and below -1/4 into your derivative. Now, here's my derivative right here in this purple box. Can you pick a value less than -1/4? Any value less than -1/4. Say -2. If you plug in -2 for x, can you see that you're going to get -7? Now, it doesn't really matter what value it is exactly. All you have to know is that it's going to be negative. Like if I plugged in -100, is it really obvious that this answer is going to be negative? Yes. And if I plugged in 5,000, is it really obvious that the answer is going to be positive? So we know this section after -1/4 is positive. And any section that's negative, if our slopes are negative, that means our function is decreasing or going down, as shown with that arrow. And anywhere that it's positive means that our function is increasing or going up. So we know that it's decreasing from -infinity all the way to -1/4, and it's increasing after -1/4 all the way to infinity. If we look at that graph, that's exactly what we see. And if we'd plug in -1/4 back into our original function, back into 2x² plus x minus 21, we would get a y value of -21.125, and that would be our vertex. In particular, this is a nice one to use calculus, because those numbers aren't nice numbers, so if you were completing the square, you'd be dealing with a fair bit of fractions in this one. And we can see, okay, this is where the arrowheads sometimes get people confusing. The arrowhead is pointing up. Does it still make sense that the red section of my graph is decreasing? Okay, don't be confused by that arrowhead pointing up, because you're going from left to right. So as I start on the left side and I'm coming towards the right in this red section, I draw a little purple dot there. Right? If I start up here, I am going down, I am decreasing until I get to my maximum, and then I am increasing after that. Oh man, Smartboard is not acting up nice today at all. Here's a cubic equation. This one, upon looking at it, you go, oh, maybe it's not something that I see as easily to figure out how I would graph it. We can talk about some of the graphing strategies we used in grade 12 to graph cubic equations, but right now we're going to start with calculus saying I'm going to take my derivative, and then I'm going to set my derivative equal to 0 to find out my critical values. And in this case, there's two critical values, at x equals 2 and at x equals -1. One of those might be a maximum, one of those might be a minimum. Now, if we set up our number line, and I always like to plug in test values into the factored form of my equation. For example, so I've put my test values of -1 and 2 on a number line. I need to test something less than -1. Most people like to choose the closest one, so they go -2. Now, if I plug in negative 2 into the factored form of my derivative, is it really easy to see that this is first bracket's going to be negative? Because negative 2 minus negative 2 is negative. I'm not going to try to remember negative 4. I'm not going to multiply everything out. I'm just going to remember that this first set of brackets is negative. By the way, 6 is always positive, last time I checked. Okay? And then x plus 1, if you plug in a negative 2 into that, can you see that that'll give you a negative number as well? And if I multiply a positive number times a negative number times a negative number, I'm going to get a positive number in this section. Second section, something between negative 1 and 2. Well, I might choose 0. If I choose 0 between negative 1 and 2, well, this, again, is always positive. This will be negative, but this will be positive. And if I do a positive times a negative times a positive, this section will be negative. And it will not matter whatever number you choose between negative 1 and 2, the same thing will always happen. You'll always get negative. Now, I chose 0 because it's an easy number to do mental math. If you really want to push yourself, you can choose crazy decimals. You could have chose 1.37 and plugged it in. Can you see if you plug in 1.37 that the second bracket is still negative because you're going to subtract 2? And 1.37 plus 1 is still positive in that third bracket. And when you multiply all those together, you will still get a negative number. And finally, if you choose something larger than 2, and you plug those numbers in, say you chose 5. 5 minus 2, that's a positive number. 5 plus 1, that's a positive number. And a positive times a positive times a positive is positive. So what I like to show when I'm showing my work is just these positive, negative, positive signs. Showing the arrows to show where it's increasing and decreasing is really helpful because you get a sense of what your graph is going to look like, even from your sign diagram. You can see, do you think negative 1 is going to be a local maximum or a local minimum? If it's going like this. Can you see that it'll be a local maximum because it's kind of peaking from your arrows? And this one is going to be a local minimum. So we can say where a function is increasing and where it's decreasing. We can draw our graph, and if we want to find exactly where that maximum and that minimum is, we can plug those values back into the original equation. So when I plug in negative 1, I get 7. And when I plug in 2, I get negative 20. Anytime you want to label points on your original graph, we have to plug in the x values into our original equation. Sometimes people think, oh, when do I plug in values into my derivative? And when do I plug in values into my original equation? When you want to find actual points on your graph, you'll plug in values into your original equation. When you want to find out where something is increasing or decreasing, that's when you plug in values into your derivative. Now, some things from last year. From grade 12, you graphed functions like this. One of the things you might have remembered from grade 12 is that an x cubed graph, if it was positive, started down here and ended up here. Could have some stuff in the middle, but you learned that a positive x cubed graph had sort of the same attributes as a positive line. As a slope going from left to right, it was increasing. Some other things that you would have learned from last year is you would have said, well, maybe I could factor this to find my x-intercepts and y-intercepts. This one factor is really nice because you can take out an x, leaving you with 2x squared minus 3x minus 12. And this also factors nice to give you, let's see, what? 3 and 4, does that give us, no, 6 and 2. Does it even factor nice? No, it doesn't factor nice. I was hoping it would, but nothing we put in there factors nice. So this part, if you wanted to solve that, you'd have to use your quadratic formula. But we could factor out an x. Now that x gives us this point right there as an x-intercept. The other ones would have, if you used your quadratic formula, told you those 2 points. Yes? Why is it a round bracket here? We always use a round bracket in English with infinity. In French immersion, you would have used the backwards bracket like that with infinity. So a notation change from English and French. The English notation uses round brackets when something isn't included. In French immersion, you used backwards brackets when something wasn't included. So in French immersion, this would have looked like this. Okay? In English, so if you were going from -1 to 2 and including it, it's exactly the same in English. This would be including. So English uses square brackets to say that it's included and round brackets to say that it's not included. French uses square brackets all the way, but if it's included, the bracket includes it. If it's not, it turns the other way, right? So what you learned in grade 12 last year is you could find your x-intercepts by factoring, and then you knew that it had to go like this through those points, but you didn't know how far or how high to make it. You weren't able to, last year, get those values. But with calculus, we can now find those values exactly. Okay, I'm going to get you to try this one. How did your derivative go? Did you get all 3 critical points? Your number line. Did it go down, up, down, up? So when you plugged in values into here, you would have got negative numbers. Go purple. Positive numbers, then negative, then positive, to show that it was decreasing, then increasing, then decreasing, then increasing. You could label where it is increasing and decreasing. And on your graphing calculator, this is what it would show up. You could find those values of your maximum and minimum points by plugging them in to the original equation. So 0, -3 is really easy to figure out. -2 is a little bit bigger numbers, but not too bad. And so our graph is already, by having those maximum and minimum values, way more accurate than it was when we were graphing in grade 12. Because in grade 12, all we had were x and y intercepts, and we knew what the end behavior was. But now we can have exact values for those maximums and minimums. I can go back. And you can start that next one. So in this function, if we do the derivative. How do we do the derivative in this case? What kind of rule are we going to use? Quotient rule. How does the quotient rule look? Keep the bottom the same times the derivative of the top minus keep the top the same times the derivative of the bottom all over the bottom squared. Now, if we simplify this, well, the bottom is going to stay x squared minus 1 all squared, but on the top, can you see that you'll get 2x cubed minus 2x, and then minus 2x cubed plus 8x. And if we simplify that on the top all the way, our x cubes cancel out, and we're just left with 6x over x squared minus 1 all squared. Now, what makes this one different than our other ones that we've done so far is that not only do we have to solve when is this equal to 0, and when is a fraction equal to 0? A fraction is equal to 0 when your numerator is equal to 0. So we're going to get x equals 0 as a critical point. Now, up until now, all of our critical points that we have dealt with have either been maximums or minimums. We're also going to find out that asymptotes or non-permissible values also affect our graph. So in this case, do we have any asymptotes or non-permissible values in this graph? Is there any place where you would be dividing by 0? Well, if we factored the original equation, the top would be x plus 2, x minus 2, and the bottom would be x plus 1, x minus 1. And so our non-permissible values x can't equal 1 and x can't equal negative 1. So if I got you to do this by yourself, when you went to your number line, the only number you would have put on there is 0, because you hadn't learned about the non-permissible values part also being critical values. But your non-permissible values, negative 1 and 1, will also happen on your graphs. And now, when we plug things in, a couple of things to note. First of all, does it make sense that the bottom of our derivative, because it's squared, is always going to be positive? So when I plug in a number less than negative 1, like negative 5, I'm really only have to look at the top of my fraction. And it's going to be negative on the top of the fraction, so I know that this part is decreasing. Another thing that hasn't happened in any of our graphs so far is things have always alternated. Went negative, positive, negative, positive. Almost made you think, does that always happen? Well, here's our first case where if you plug in a negative number between 0 and negative 1 into this equation, we're going to get negative again. So it goes decreasing twice in a row. Between 0 and 1, it's going to be positive. And between 1 and infinity, it's also positive. So what does this graph look like? Well, we would have asymptotes at negative 1 and 1. At 0, we're going to have a local minimum. Can you see that you are decreasing from negative infinity to negative 1, or from negative 1 to 0, and we are increasing from 0 to 1 and from 1 to infinity. Some other things from last year. Do you remember how to find horizontal asymptotes from last year? Horizontal asymptotes are looking at what happens when x gets to really large positive numbers, or what happens as x gets to really large negative numbers. One of the things you might have done last year is said, well, my highest power in f of x is x squared. So if I just look at my x squareds, I'm going to have x squared over x squared. That simplifies to 1, and that's why we have an asymptote at y equals 1. Now the rest of this graph would have been a little bit harder to graph, but now we know where our minimum is in that section in between. And if it is, now this is the powerful thing about the sign diagram. If you're starting at negative infinity and your graph has to be decreasing, the only way that's possible is if you start below the asymptote. Does that make sense? So that you can go down towards this one. And then after negative 1, it's still decreasing. The only way that works is if you started up here and came down to 0, 4, and then went up afterwards. And in this section, if it's increasing from left and right, it has to start here and go towards our asymptote. Last year, what you would have done is just plotted a bunch of test points in those sections to figure out, oh, it needs to be below the asymptote or above the asymptote. All right, I'll get you to try this one. So first of all, we took our derivative, no problem. Get 6x squared. Set that equal to 0, and we get only x equals 0. Make our number line, and it's always positive. Again, we only put our critical value or non-permissible values on our number line, so the only value that goes on there is 0. And when we plug in anything into our derivative is 6x squared. Doesn't matter if you put a positive number or a negative number into x squared, you will always get something that's positive. So this is increasing then increasing. So that feels a little bit weird, because then up till now, any time that we've had a critical value, it's either been a maximum or a minimum. And our arrow diagrams, it was easy to see from our arrow diagrams if it was a maximum because it went up and then down, or if it was a minimum because then it went down and then up. But this one is going up and then up. How does that show up in the graph? Well, if we go back, because this one's always increasing. Increasing forever. Now, if we go back to grade 12 and we say, hey, this is actually one I could graph using transformations. I know what an x cubed graph looks like. The 2 in front would stretch it vertically, and the 5 would move it down 5. So this would be the graph that I would get. What we have at 0, -5 is a situation where the tangent is flat. So your x cubed graph flattens out at 0, -5, but then increases again. So when we're drawing that, we imagine it, the slope's flattening out and then going back up again. And that's why our x cubed graph has that shape to it. actually flattens out completely at that point. And so this isn't a maximum, it isn't a minimum. We're going to give this a name later. We're going to call this a stationary point of inflection. It's a nice, easy term to remember, right? What we're going to find out is we use the word stationary point to show when something has a horizontal tangent. So maximums, minimums, and these points are stationary points. Because temporarily, your object is stationary. Like if you throw an object up into the air, there is a point where it reaches its maximum, and at that moment, it's stopped. For that little second, it stopped from moving upwards to moving downwards. And so we say that it's stationary at that point. This one is always increasing, but there's a moment in the middle where it stops and then keeps going up. So we say that that's a stationary point. The reason we use the word inflection is we are going to use the word inflection when a graph changes concavity. Concavity refers to whether something is concave up or concave down. Concave down is whenever something is like that. And concave up is whenever something is like that. Can you notice on your x cubed graph that that stationary point of inflection, before it, it's concave down, and after it, it's concave up. So because it changes concavity, that's called an inflection point. These are all terms that we learn throughout this unit in curve sketching, but we get introduced to them here. And so it changes concavity, and it's stationary at that point, so that will be called a stationary point of inflection. A couple more examples we're going to do, and then we're done for today. So the y-intercept is 0, 7. We've got our function there, a e to the kx plus 2. Show that a has to equal 5. So you have to use the information that you're given and solve for a. Well, the only thing we're given is 1 point and the equation. So does it make sense to plug that point in? And if you plug that point into that equation, the k doesn't become a factor because k times 0 is 0. And e to the 0 is 1. Solving for a gives you a is equal to 5. And part B, if we're told that f of 10 happens to be roughly 2.67, could we find the value of k? Well, we already know the value of a is 5. All we need to do is plug in 2.67 for y, and we're solving for k. How do you solve for k in exponents? Well, I guess if it's a calculator question, you could graph both sides and find out where they intersect, or you could go back to your logarithms. Right? Whenever we're solving for something in an exponent, we can take the logarithm of both sides. The natural log of e to the 10k. Again, here, you could use log or natural log. Natural log is nice because the natural log of e is equal to 1. And so that's why it's canceled out in that second last line. Solving for k, we get approximately negative 0.201. So now that we have the value of a and the value of k, we can go to part C, find the derivative. Good, ready? So we've plugged in our value of a and our value of k. Our derivative is a chain rule. Our outside function is e to the x. The derivative of e to the x doesn't change. That's why we still have 5e to the negative 0.201x. Then the chain rule says, what's our inside function? Our inside function is negative 0.201x. What's the derivative of that? Just negative 0.201. Simplify it if you like, and we've got our equation of our derivative. Something that occurs a fair bit is an understanding of e to the x. Do you know that y equals e to the x looks like this? That no matter what you plug in for x, it's always positive? So if e to the x, no matter what's in there, is always positive, then if we multiply that by negative 1.005, we're going to find out that it's always going to be negative. Because that negative 1.005 out in front causes it to be negative. Again, thinking back to our graphs, do you know that the graph of y equals e to the x has a horizontal asymptote at y equals 0? The only way that that asymptote would change is if you did a transformation that shifted it up or down. Since nothing has shifted it up or down, oh yeah, there is a shifter up or down at +2 for f of x. I was looking at the derivative. So looking at our original equation, sorry. Can you see in our original equation that we have shifted it up 2? So if an e to the x graph has an asymptote at y equals 0, and you've got a vertical translation of 2 units up, you are now going to have a horizontal asymptote at y equals 2.